methods and the collaboration of the ISOs in the US, and trying to see how the PMUs can scale up to a really big system. And then the next question I want to report is, all right, how do I use that diachronics moment? Okay? And to use that, obviously, I want to use that so when the system is in trouble, it will tell me something, right? So how am I going to use that? But before I can talk about that, I will say a few words about the reconfiguration of power grid, which is one of the so-called defense actions. So if the system is really in trouble and you don't have better alternatives, one way is to split the system. And when you split the system, then hopefully the major part of the system will survive, and the disaster will not propagate too far to the entire grid. So that's why this is one of the self-healing actions that people have been studying. So here is an example to show if the system is in trouble, I can split that. So this generator serves that load, this generator serves that load. And of course, generally, if you interconnect them, it will be more stable. But if you don't have a better alternative, maybe splitting is not a bad idea. Okay? So we have this algorithm that's called multi-level graph partition. This is just, I will just say, this multi-graph partition, what it says is this. Why do I need partition? You know, traditionally we use a special protection scheme, SPS. And SPS is for very specific scenarios. So I look at particular line, particular relay. If a particular scenario occurs and it meets all the criteria, then relay trip the breaker and the system is split. That's SPS. But when you look at the defense system, it has to be more general. It has to be smarter. And so what is a smartness? So one of the smartness is to say, okay, fine. I will look at a big grid and I will find where you should partition for the condition now. All right? Which means it's not fixed. Because if you do it for a fixed scenario, if that scenario does not happen, your system cannot happen. Right? And so we want to be able to determine where the partition should be in a more flexible manner. And this algorithm, we are using this algorithm because it's really fast. This 2012 plus, I think this is the eastern part of the US, that's a model. And even for a big system with very, very primitive computer, it takes only a fraction of a second. So computation is not the bottleneck. The bottleneck here is the hardware, the communication, and how you actually determine where to put that and make the system work. So algorithm and computation does not seem to be a major stumbling block. So this partition here, the partition we have here is to use real power and reactive power. So I will explain what this means. So we take a big power grid, and I want to study partition. And you can partition the grid into 2 or 3 or 4 or any number you like. Right? You tell me the number. Okay? And if you tell me the number, I will find those partitions. And when you partition, the objective is to make sure after partition, these partitions will be able to survive on their own, which means the supply demand for each partition should be more self-sustaining, right? Which means the interchange, the exchange of real power and reactive power between partitions, between items should be minimized. And so we take a real power partition, reactive power partition, and somehow weigh it together and create one partition that considers both. All right? Now, and so now I have a way to find that partition, but I have to decide when do I do it. That's the biggest question. All right? When is the system bad enough that you are going to trigger that partition? It's going to be a major decision. So, and it's unlikely that you can decide, you can decide in the offline. You have to do it in an automatic control mode, because when things are happening, it's going to happen fast, and there's no time for human intervention in this. So what we are trying to do is to use that diagonal exponent I mentioned as an index. And I want to use it to predict an unstable condition and use that unstable condition to determine when to split the group. So that's what this is all about. Okay, so this is the implementation. So let's look at this example. That's probably more interesting. So here is that system again, and you will see some partitions. Actually, there is a partition. This dotted line. This is the final partition of the group, and it's going to follow. And that partition will minimize the weighted sum of the real power and reactive power exchange between the two partitions. Okay. All right. So here is a system, and this is what's happening to the system now. So something T0 line trip. So line trip, whatever reason, 3 line trip. At 60 seconds, another line trip. So this is line fault, and then 120 seconds, another line fault. And when you begin to lose line like this, you have reactive power problem because the voltage begin to drop, right? One generator number 70, become overloaded. So it's clear that the reactive power load is becoming very high because you're losing lines. And the generator has to provide reactive power to support the voltage. So it looks like a problem. And then at 240 seconds, generator 70 hit the limits, field current limits. This is the field current limits, not the, so this is the generator rotor field current limits. When you hit the limits, to be more precise, it has to be a temperature limit. But let's say field current limit is one way to start. So we have the field current limits, and it's tripped by overexcitation protection. And then you can see from the diagram, after 240, this is 240, 241. After 241, it generated trip, and then you can see everything collapse. After 20 more seconds, everything collapsed. Okay? And so we calculate the maximum diagonal exponent, and so the interesting thing is the system partition is initiated at 241 seconds, and 1 second after tripping of that generator. So before you trip the generator, you don't know what big thing is coming, so it won't make sense. But after generator trip, your question is, how bad is it? Is it a major impact that's going to pull down the whole system, or is it something the system can tolerate? That's the decision. And so if you actually calculate the diagonal exponent, it says it's going like this. This is this angle difference, but the diagonal exponent has that same. Let me see, where's that diagonal exponent? Yeah. Anyway, the diagonal exponent has been negative until 241. So when you calculate 241 in turn positive, that's the instant where you decide it's bad enough. It's instability problem, and we better partition the system. Okay, so after partition, this is simulation. To say that 241, if you actually take that contraction at 241, which is somewhere here, then the system becomes stable, and you have two islands. There's a north island, a south island, and both become stable after that tripping. So I think what's new here is to bring the two things together. Partition is not new. That's been somewhere. Okay? PMU is not new. But use the PMU to look at the control action and say, when do I take these actions? That is the important part of this. So this is something that I thought might be of interest to you. And then we test the big systems by partitioning, as I said. Partitioning itself, computation is not the problem. So let me then talk a little bit, spend a few minutes on the the next question of self-heating. We are still in self-heating, right? So what can I do about self-heating? Can I avoid that generator tripping? That's the question. G number 70, right? Generator 70 trips because you lose lines and electric power problems. Is it possible to avoid that kind of problem? And that is the self-heating action. And the next piece is to tell you a study that says, well, if you look carefully enough, and if you know, if you can do some more calculation than what we usually do, perhaps you can find a field current of a generator and begin to develop some insight about what might happen. And some simple control actions might help you actually prevent something serious like this. So this picture says, if you begin to lose lines, like here, you lose lines, then generator reactive power, if you lose this line, this voltage comes down and the reactive power demand will increase. Then if you lose the generator because of the overexcitation protection, then this one burden is increasing. And so this one will send more reactive power and you have cascading problems there. And a scenario like this, you can find it in the literature. I actually brought this scenario came from the literature of the voltage collapse scenario. So the question is, am I able, if I know the generator is going to trip, is there a way I can avoid it? Okay. That's a self-heating action. And so here is this is a protection picture. This is the overcurrent protection. So it's actually an overcurrent protection of the field, of the rotor field. So normally we don't do that, but we are talking about self-heating in the future, right? So if you monitor, if you know the field current, you can calculate the field current of the generator. Then maybe you can find a way to avoid relay tripping, overcurrent tripping, because you might lose the generator there. You should use other control actions. So this is the overcurrent relay characteristic. If the fault current is high, if the fault current is high, time is short. Tripping time is short. If the low fault current, tripping time is long. It's the inverse time characteristic. So let me show you this picture. So what is the idea? The idea is this. We are already doing a lot of computation now. We're doing security assessment now, right? So we do a lot of power flow, different versions. And today it's feasible. We just solved the nonlinear power flow for many contingencies. That's all feasible. So we are already calculating the power flow. But we are not worrying about the cascading events. So because we are more tied to n-1 security, n-2. And so if you're able to take that power flow results, then I know the generator power outputs at the generator bus. And I take that information from real-time computation of the contingencies. These are contingencies, not necessarily real measurements, right? Take that, work backwards into the power plants and calculate the field currents. I'm sure you can pull out the textbooks and you get all kinds of equations and the student will enjoy that. You take that equations and take the terminal conditions from the real-time computation, work inside the power plant, figure out the field currents. And from there you can get a lot of interesting information about what might happen to this generator. Right? We don't do that. And you can do the same thing for the relays. If you take the power flow result and then bring in the relay data, it can help you with the impedance relay, zone 2, zone 3, that kind of things. That's also another way to avoid cascading events. They are also part of the self-healing functions. So the idea here is take the real-time contingency results, power flow, do a little more work, get into the power plant, calculate the field currents, and that will give you more information about the protection, the overexcitation protection, and whether or not the generator will trip. So now there's another issue here though. The problem is the online calculation is steady state right now, right? And the real system is dynamic, and so there is a discrepancy. So this picture says, if you actually compare the time domain simulation with just the steady-state power flow, they will give you different results, somewhat different results of the field current. So this is based on steady-state power flow, and this is the field current based on the time domain simulation, dynamic simulation. So how do I bridge that gap? So one way is to do some artificial intelligence, do a lot of simulation, and try to generalize and collect some rules out of it. And that's why there's a term of fuzzy inference system there. And so what it means here is I'm doing the correction of between steady state and dynamic. That correction, I'm using some offline terms to try to get close. Okay. All right. So then, of course, if I need to do a fuzzy inference system, I will need to do some training. So here, so I need to have some training and input outputs of the fuzzy inference system. Do some simulation to create a data set for training and data set for testing. So let's look at the 200 bus system again. Now this time my self-healing action is I'm trying to see the generator problem early enough that I'm trying to do something so it will not happen. That's the smart self-healing. Alright? So here is the system again. And I need some training data set I mentioned. And validation cases, I need some cases for validation. And I don't need to talk about it. So case 1. So in this case, we see the relay characteristic again. This is the overcurrent protection part of the generator, of the excitation of the generator. So it should be get more careful. So if you look at overcurrent, there's a threshold. This dotted line is the threshold. And if I can calculate it 3 ways. One is just do steady-state power flow, and that will give me a field current here. And this current is well above the threshold, and so that means it will trip, right? It will trip. And these two are very close, also above the threshold, and so they will trip through. And the tripping time is close. This time domain simulation and the fuzzy inference system correction. This triangle and the diagonal. So this tells you that correction is contributing, is making them more accurate, right? So, but this is one way, which means now I can, based on this, I can see whether the relay might trip, right? You give me the contingencies, I take the result, feed it to the different kinds of power plant, do more calculation, it will come back and it tell me, based on this relay characteristic, which power plant might be in trouble, right? This is the purpose of that. And the other case here is, here's a steady-state power flow. It says here, this generator excitation protection will trip that generator. The other two is the triangle and the diamond. They were below the threshold, which means the more accurate result is this relay will not trip, right? If you just do steady state to try to predict something dynamic, in this case it shows it doesn't work all the time, right? So this is an interesting case. But then probably the most interesting thing is this one. So this is the most important result of this, I think, this part. The G47 tripping can be prevented by reducing terminal voltage from 1.05 to 1.02 system power system. So what it says is this: we are doing contingency studies, right? And for one contingency, I figure out the field current, there's an overcurrent in the field circuits, so I might lose that generator, right? But if I can change my operating condition by less 3%, 0.03, per unit of the voltage. I will calculate, I will shift that operating point, and that generator will not trip. Okay? So we don't do that right now, but this is something that's very simple, and it's not a technology. It's not the barrier. The barrier is are you going to do it? Because the computation is not that sophisticated, and so this is an interesting example to show that we are looking at power grid. You have contingency, and in the past we are more passive. We deal with insecure problem, but the major flaw is we are not looking beyond that one contingency or two. And this is saying look beyond that, because when you analyze all these blackouts, you have all these relay problems and generator tripping, creating cascading failure, all that. What are we doing about that in this next generation of smart grid? And I think this is an example to show. When you look far enough and then begin to look at the cascading effects, and that's what will make the grid a little bit more smarter than before. I think I'm a little bit out of time. So that's my report. So, if you are interested in some papers, I think with this I will finish my report. I don't know. I think we have time for questions. Maybe at least after the discussion, so we can open up all other questions.
但是我们的午餐时间，上午的论坛到现在这边告一段落。